This resource is the second in a 5-part series on vectors. Part 1 defines vectors. The component form for a position vector is presented with an example. We also discover how to find the magnitude of a vector. Part 2 considers basic operations with vectors. We look at adding and subtracting vectors in component form with examples. We also consider scalar multiplication of vectors. Part 3 considers writing the vector in terms of its magnitude and direction. Part 4 describes how to find the resultant force when two different forces act on the same object. Part 5 looks at the dot product of two vectors, looking at multiple examples, including a word problem. In short, we can do operations with vectors. Vectors can be added, subtracted, and there are a couple of ways of multiplying them. We can multiply a scalar by a vector, oddly enough called scalar multiplication. We can multiply a vector by a vector using the dot product, which we will explore in Part 5 of this series. But how exactly do we do these basic operations? We have to consider the vectors written as position vectors. To add vectors, we simply add the coefficients of the unit vectors I and j. Subtract the coefficients to subtract vectors, but we have to be careful about order. Scalar multiplication is achieved by multiplying each coefficient by the scalar quantity. While we call these operations on vectors, we are simply combining like terms, or using the distributive property. Let's look at an example. Suppose we have the vectors v equals 7i plus 3j and w equals 4i minus 5j. We want to find the sum and difference of the two vectors, and also the result of multiplying vector v by the scalar 5. Let's look at the sum of the two vectors first. To add the vectors, we combine the coefficients for I and the coefficients for j. So we are combining the 7 and 4 in the x direction and the 3 and the negative 5 in the y direction. This gives us a new position vector, 11i minus 2j. Now let's try subtracting the vectors. If we subtract v minus w, we have to subtract the coefficients for I and j in that order. So we have the quantity 7 minus 4 times I plus the quantity 3 minus negative 5 times j. So the difference of the two vectors is the position vector 3i plus 8j. When doing scalar multiplication, we multiply the entire vector by the appropriate scalar quantity. So if we want to do 5 times v, we have to multiply 5 by the entire 7i plus 3j. This gives us a final answer of 35i plus 15j. We can also combine the ideas of adding or subtracting vectors with scalar multiplication. This leads to a more complex operation, a linear combination. We do not have any new techniques to discover. We just do all the work we have done before. Let's look at an example. Suppose this time we have vector v equal to 9i plus 7j and vector w equal to 3i minus 2j. We want to find the linear combination based on these two vectors of 4v plus 6w. First, we will worry about the two scalar multiplications. We multiply 4 by all of vector v and 6 by all of vector w. This leaves us with 36i plus 28j plus 18i minus 12j. Now we will combine our like components, so I with I and j with j. So our linear combination is the vector 54i plus 16j.